What I'd like to do now is try to demystify Hubble's law. Hubble's law is this equation here. The velocity of a distant galaxy is generally equal to Hubble's constant times its distance. And most people think that that represents some kind of new idea, but basically if I just divide both sides by Hubble's constant, we'll get distance equals 1 divided by Hubble's constant times velocity, and in fact 1 over the Hubble's constant is just the age of the universe. So this is actually the equation distance equals velocity times time. So we know a couple of things. Hubble's constant is 72 kilometers per second per megaparsec, and the age of the universe we're usually given is about 13.7 billion years. So what I want to do is show you that 1 divided by 13.7 billion years is equal to 72 kilometers per second per megaparsec. So what I'm going to do is start with 1 over h naught, which is 1 megaparsecs divided by 72 kilometers per second. I'm going to multiply that by 3.26 million light years per megaparsec. Multiply that by 365 light seconds per light year, 24 light hours per light day, 3,600 light seconds per light hour. And I come up with 1.39 times 10 to the 12th light seconds per kilometer per second. So I'm going to take that figure and multiply by the speed of light 3 times 10 to the 8th meters in 1 light second, and 1,000 meters in 1 kilometer, and I come up with a somewhat disappointing result of 4.178 times 10 to the 17th. Well, okay. It's only disappointing because it's not done yet. This is in seconds, so I still need to fix it so that it is in years, right? So I'll use that 3,600 seconds in 1 hour, and there's 24 hours in 1 day, and 365 days in 1 year, and we get 1.32 times 10 to the 10th, or 13.2 times 10 to the 9th years. Now, there's some rounding errors in this, but it's pretty close to 13.7 billion years. Which is commonly given as the age of the universe. Now if I draw a space-time diagram with space going this way and time going this way, and I imagine something going out at 72 kilometers per second, we should expect that the distance from it now after 13.7 billion years would be 1 megaparsec. If it went off at 144 kilometers per second, then it would be at 2 megaparsecs. If it flew off at, what is 3 times 72? If it flew off at 216 kilometers per second, here, after 13.7 billion years, we would expect it to be at 3 megaparsecs away. And that pattern should continue on and on. So, at 10 megaparsecs away, we should find galaxies traveling away at 720 kilometers per second. At 20 parsecs away, we'll find galaxies traveling at 1440 kilometers per second. Now we're going to have a little bit of a problem when we get to velocities that are approaching the speed of light. I could probably do a whole series of videos on how astronomers estimate the distance to galaxies. Most of them revolve around finding the luminosity, the expected, versus the observed. Let's say you know or you see a star or a galaxy, and you identify it. Basically, you figure out what kind of star it is, and if you can figure out what kind of star it really is, that means you can determine how bright it really is. Then you want to compare how bright it really is to how bright it looks, and from that you can calculate how far away it must be. Now, from these luminosity comparisons, they've found that they think that the farthest stars from us are around 40 billion light years away. But that's a problem, because if those things are 40 billion light years away, and the universe is only 13.7 billion years old, the largest distance we should observe is this 13.7 billion light years. Now, there are some resolutions to this problem that have been proposed. The main one is called inflation. But I want to suggest an alternative hypothesis, which is to say that there are two different events involved here: an original Big Bang and some later Big Bang. A Big Bang, but not the Big Bang. For now, I'm not going to go into the details of special relativity, but just kind of understand that there's basically going to be two different Hubble's constants involved here. One of them, the Hubble's constant involved with this, is 1 over h naught equals 1 divided by 13.7 billion years. And then there's going to be an outer Hubble constant that is going to be h naught, h1, equals 1 over 40 billion years. And these two Hubble's constants, it might not be completely symmetrical. For instance, maybe the system looks a little bit more like this, in which case there might be a 30 billion, 1 over 30 billion over in this region, 1 over 14 billion, 1 over 14 billion in this region, and maybe 1 over 40 billion over here in this region. Another reason that I would suggest this kind of pattern is because it would create a little bit of an asymmetry. If I looked in that direction, I would see the universe as it existed, or the edge of the universe as it exists at this time here, T1, and if I looked this way, I would see the edge of the universe as it existed at this time here, T2. So you see a different epoch as you look in different directions across the universe. Now, the reason that I want to have an asymmetry in this thing is because I want to have an explanation for what's called the cosmic microwave background radiation dipole anisotropy, which is basically just the difference between the temperature of the radiation of the edge of what's like the edge of the universe in two different directions. Now, that pretty much wraps up what I was going to talk about, but I did want to hit this point before I go. I could make that calculation of conversion from Hubble's constant to the age of the universe much easier by using this conversion factor here. Using this, I start with 1 kilometer per second per megaparsec, or the reciprocal of that, times, I want to use Hubble's constants, which is 72 kilometers per second per megaparsec, and multiply that by 3.1 times 10 to the 19th kilometers per megaparsec, which gives you 4.3 times 10 to the 17th seconds, and I want to multiply that by about 3.15 times 10 to the 7, seconds per 1 year, which gives me 13.6 billion years.